Welcome to the Absolute Simulations demo. The objective of the Absolute project is to design aerial terrestrial networks capable of supporting reliable high data rate applications, to serve large-scale disaster emergency situations and temporary event scenarios. The Absolute architecture is based on the following elements: multi-mod user equipments, aerial base stations, portable land mobile units, and satellites. The main objective of the simulation framework is to model the Absolute network and protocol architecture, in order to measure the key performance indicators for the dimensioning of the lab testbed and related comparisons. First, we explain the packet-level simulations, which reproduce the Absolute network scenarios using the aerial E-Node-B model, evolved packet core model, user equipment model and complementary models, for simulating the LTE stack. As an addition, a satellite link simulator is also included, in order to model the different phases of the Absolute network deployment. The models are implemented using OMNet++ simulator, in which source code and graphical interface allowing to explore the source code of the models like, for example, the aerial E-Node-B, user equipment, evolved packet core, audio and video generator servers and channel controller. The aerial E-Node-B is composed of the LTE interface, the light EPC, namely flexible management entity, and wireless interfaces used for backhauling. In the LTE interface, the complete LTE stack is implemented, where modifications are allowed using the source code files. The user equipment model also contains LTE interface and UDP-TCP packet generator models. LTE stack for user equipment side is also implemented. Thus the Absolute scenarios can be simulated using the network configuration file, which allows to set up parameters regarding channel control or the network topology. Consequently, different network scenarios can be easily created by changing the different parameters, as for example, the channel and LTE specifications. Once the scenario has been set, we can run the simulations and visualizing the different events on the graphical interface, as shown in this example. The simulations can be interrupted at any time for analyzing the events step by step. The advantage of the simulations is that the scenarios can be easily adapted, like for example, the number of users, user distribution and user mobility. In this example, the video packet generation can be visualized and explored, in order to check which information the packet is carrying. Once the simulations are completed, result files are created, which allows the user to visualize several results and statistics. The results allow analyzing the Absolute system performance working under different constraints. In this way, different conclusions about capacity, coverage and quality of service of the Absolute network can be observed. Absolute network performance is also analyzed using MATLAB system-level simulator. The MATLAB simulator is structured of several modules interconnected between each other. Each module is designed on order, to simulate specific functionalities like for example propagation conditions or spectrum awareness. Thus the simulator follows a specific process, where several modules are interacting with each other in order to produce the results from different In MATLAB programming interface, the implemented modules can be visualized. The modules include channel models for aerial E-Node-B/S, traffic models and complete set of models for simulating the Absolute architecture. In order to configure a simulation, specific configuration files are created. Inside these files, the parameters for reproducing a specific scenario of the Absolute use cases are set, as well as the source code for interconnecting the different models. When the configuration file is set, the simulation runs following the system-level simulation framework, and produce several results, that are used for analyzing for example the Absolute network behavior from an interference point of view. Finally, a specific radio propagation simulator will be used for analyzing absolute network from the coverage and interference point of view. GRASS is a free and open-source geographic information system software suite. Radio Planning Tool for GRASS is an add-on for GRASS for radio signal coverage computation. RawPlat consists of a set of GRASS modules for radio coverage computation. The first group of modules computes signal loss according to the different propagation models. Next, the R sector module modifies this loss according to the antenna radiation pattern. Finally, the R max power module computes the complete coverage map. The RRadCov module takes the burden of calling each individual module from the user by calling them automatically as needed. Before calling RRadCov, the user must prepare a table describing the transmit network configuration. Then the RRadCov module is called with parameters specifying this table, the input DEM map, the optional clutter map, and the transmit frequency. After the computation is finished, the intermediate results are also available, for example the model losses for the first transmit location, for its first antenna, or second antenna, or the second location's first antenna. And, of course, the complete coverage map is created showing the color-coded received signal strength in dBm. In this example, the computation was limited to 2 km around the transmitter. The next example shows the same transmitter configuration with computation radius increased to 20 km, and with the received signal strength threshold set at -125 dBm. Suppose that we want to add an additional emergency transmitter carried by a low-altitude platform. In this example it is 300 meters above ground and uses a non-directional antenna. The newly computed coverage area is much larger. For the Absolute project, a specialized GUI interface for RawPlat is developed and the whole package prepared as a virtual appliance for standalone use. Thus, using the simulation's results, coverage achieved by Absolute system is analyzed as well as the interferences map. For more information about Absolute project, please visit Absolute webpage.